work. And today I would like to talk about, as you can see from the title, not deep learning, but maybe shallow learning. We have to do different. I mean, it's still related to deep learning, but we use relatively few layers in our network, so therefore it turns out that, for example, if you use particular layers, like a CRF can also be seen as a layer that you can get rid of many layers. When you compare this, what we are doing, to recent, really deep learning approaches for stereo and motion, then they use, I don't know, 50 layers and millions, tens of millions of variables, and compared to that, our thing is really very shallow. It is joint work with Patrick Knöbelreiter, Gottfried Munder, 2 PhD students, and also Alexander Schekovtsov and Christian Reinbacher, 2 former postdocs. So let us consider a very classical problem in computer vision, which is 2-frame stereo. And if you have calibrated images, rectified images, it's well known that the disparity and therefore the depth in the scene can be computed by finding corresponding pixel locations. And if you have real images, this can be a hard task because you have a lot of artifacts, you have untextured areas, you have viewpoint changes, homogeneous regions, the illumination might change, you have specularities, you have shadows, over-under exposure, and so on. So therefore, it's somehow clear that in order to find corresponding points between here and here, you need somehow robust descriptors that can cope with all these different artifacts. And looking to the literature, there's one particular descriptor, local image descriptor, that turned out to be very successful, which is the scale invariant feature transform of David Lowe. You can see it received more than 36,000 citations in 12 years. When you now check it, I guess it will already have 40,000. And it's based on, I would say, clever insights on the concepts of vision. And basically what it's doing, it computes gradients, and then it computes histograms from that gradients and does some normalizations. And so it turns out to work very well. So it can cope with viewpoint changes, illumination changes, and so on. So it works very well. But it's still, I would say, relatively simple. And in 2012, there was a breakthrough paper of Grzewski and colleagues, where they actually showed that when you replace the Sept features, and they used also at that time other features, Hawk features and color and so on, when you replace them by learned features based on deep convolutional neural networks, that you can really get a huge performance boost. So it's somehow clear you replace something handcrafted by something that is learned from data. And why it does work so well is because it not only uses one layer that deals with gradients, like in the Sept. This would be, for example, the first layer of a neural network, but then based on this representation, it computes a higher level representation, and so on and so on. And so it can learn much more invariances of images than the Sept can do. And therefore, it's also clear when you want to do stereo or motion, you can expect that replacing handcrafted descriptors like Sept or tensors transform and sum of absolute differences or whatever has been used in the past, you can, if you replace it by learned descriptors, you can get better results. And exactly this is what we want to do. We want to learn better descriptors for motion and stereo and use it in an energy-based framework in order to do motion and stereo. When you look at recent benchmarks, so for example for stereo, there's the Middlebury stereo benchmark, and for optical flow, there's the Sintel optical flow, which is based on a synthetic video. When you look to the top performing methods, for example, in stereo, everything has been learned. There's just one guy that still uses sensors here in one of the top performing methods. When you look to the benchmark of optical flow, then you see learning is only barely used. So there are just a few approaches that use learned descriptors, and the rest is still based on handcrafted features. So first, what I would like to do is, I would like to talk about the stereo model, which is based on labeling discrete optimization. And then I will show you how you can do learning in order to get better descriptors used in the stereo model. And then I will go over to motion. So I still believe, I hope you agree, that the best performing stereo models are still based on energy minimization. So when you look to these benchmarks, There's a lot of engineering involved, but usually at some point some energy-based method is used in order to get a final solution. So what we are using here is a classical model. In computer vision it's called conditional random field. The idea is the following. So here consider this is an image. This node corresponds to the image pixels, and we want to assign to each node a certain label. For stereo it will be just a disparity, so it can be from 1 to D. Typically D is around 200 for practical stereo problems. And for each of the label assignments, for each node we will have a certain energy that is based from descriptor matching. So when we do an exhaustive matching of descriptors of the left and the right image, for different disparities we will get distances between the descriptors, for example like correlation, and this will go into the so-called unary terms, and this is multiplied here. So Fi is the unary term for the vector xi, and xi is a one-hot encoding of the disparity. So it means, for example, when you look here, so if the disparity is 1, the vector will be 0, 0, 1. If the disparity is 2, it will be 0, 1, 0, and so on. So it uses a one-hot encoding. And since we want to have smooth results, we can also use a smoothness prior that compares the labels of neighboring pixels. And here we use a simple for neighborhood. So and the smoothness term is here represented via edges between different labels. And the idea is, of course, to find a certain configuration X, so a certain labeling of this energy that minimizes this energy here above. So unary terms and pairwise terms. If you want data term and smoothness term. Okay, so in order that this one-hot encoding makes somehow sense, of course, we have some integrality constraints. So X should be an element of 0, 1 to the power of D. So just one of these vectors here can take the value 1, the rest has to be 0. And this is expressed by this thing here. So how do we plan to compute the matching term? So here what we're doing is we have two parallel neural networks. So one is applied to the left image and the other one is applied to the second image. And it simply uses convolutions and nonlinear operations, so just 3 to 7 layers, so relatively shallow. And the output of this neural network is a feature descriptor for each pixel in the image, similar to computing a dense SIF descriptor. And usually we use a feature dimension of 96 or 64, so it's quite a huge vector. And then what you're doing is you need to compare the feature vectors of the left image and the right image exhaustively for each disparity. And this is expressed with this function. So this function phi can be simply an inner product, or it could be a L1 norm or quadratic distance, whatever you want. And when you do this exhaustively for all different disparity, what you have in the end is a cost volume. So it has the size of the image times the number of different layers. So it tells you for each pixel in the image what is the cost for a certain disparity. Since we use just 5 to 7 layers, our CNN has relatively few parameters, so a few 100,000 parameters approximately. When you compare this to other really completely learned deep networks, they have millions of parameters. So what about the smoothness term? So here in the smoothness term, we take standard stuff, so it's more or less a truncated total variation if you want. Just here it's piecewise linear, so to favor relatively small slanted surfaces. And additionally, we penalize, or we weight the distance function h, so h is this function here, between label difference. We weight it with a function that is derived from edges from images. You can do classic stuff that is that you say, okay, at strong gradients in the image, this function should be very small to favor discontinuities of depth or motion at image edges. Or what we do here, we also learn this function from the image. So we also have a small convolutional neural network that takes the image as input and outputs a weighting function, and this will later be learned together with the CRF. So in order to make everything work, it's known that neural networks are quite efficient because they use so simple operations. The whole story only makes sense if you can also solve the 0f efficiently. And it's actually not an easy task because consider if you solve the 0f for an image, you have size of image times number of labels. This is your problem. So you have to solve a 3D problem. And it turns out the algorithm I will now describe, which is very efficient, can do this in less than 1 second for relatively large images, so 1,000 times 500 times 300 labels, for example. So let us first review some state-of-the-art algorithms that can be used to solve this kind of 0f. So maybe the most standard one is to derive the LP relaxation. And this dates back to work of Michael Schlesinger in 76. What you simply do is you drop the integrality constraint and make a simple relaxation to the unit simplex, and then you can solve the resulting problem with an off-the-shelf LP solver. This may not be very efficient, so using standard LP solvers, I guess even you cannot compute the solution. It's too huge, the problem. But basically, you can compute the solution with that approach. So another approach is max product belief propagation. Dates back to Pearl 88, which is known to be exact on trees. But here we have a grid with cycles, and for this type of approach, it's known that if you have these loops, it can yield inferior solutions, or it can also may not converge or may get stuck or whatever. So it's not guaranteed to converge on loops. Then there's a whole class of so-called move-making algorithms that have been popularized by Yuri, by Vladimir, by Olga, and co-workers. And the idea of those algorithms is you solve a sequence of simpler binary problems, and the sequence of binary problems are supposed to increase, or in the primary problem, to decrease monotonically decrease your energy. If you have relatively few labels, this works very well. For example, for the POTS model, it really works well. But here in stereo, we deal usually with 300 labels, or in optical flow, even more labels, and then it may not scale so well with such large number of labels. Then there's an algorithm which is called tree-related message passing, TRW, Wainwright, Yaklo, and Wilsky, 2005. And the idea of this algorithm is to decompose the grid into trees. Trees could be, for example, chains, horizontal and vertical chains. Then you apply belief propagation to those trees, and then you try to get an agreement of the solutions of the tree solutions, for example, via averaging. So this algorithm works much better than belief propagation, but the problem of this algorithm is that it may not converge, so it may even diverge. I think there are some counterexamples where it doesn't work so well. And actually, this was one of the points where Vladimir picked up, and he proposed a sequential version of TRW, which is called TRWS, as for sequential. And his version has the striking property that it monotonically improves the dual energy. Okay, so it is guaranteed to converge, although it solves, it can be seen as a subgradient method or a gradient method on the dual problem. The dual problem is concave piecewise linear. It may get stuck in a non-optimal solution. That's still one of the problems. But when you look at benchmarks where this algorithm is applied, it's still, I would say, one of the best methods. And it's also very efficient, because one of the properties of this algorithm is that you make a coordinate-wise ascent, but in order to compute the coordinate-wise ascent, you can reuse messages of the dynamic program that has been already computed, so each update is very cheap. So let us look at just one chain. So the later idea will be to decompose our image into horizontal and vertical chains. So if you just want to solve one chain, then so in our example, the chain has length n, and we have d labels. So this is n, and d is the number of labels. So it's well known there are a lot of algorithms that can solve the problem on a chain. You can simply use Dijkstra's algorithm. You can Viterbi's or belief propagation algorithm, and for those algorithms, they can compute the exact solution in number n times d squared time. So general, it cannot be improved. However, since our smoothness function is of a particular form, so it's based on the differences of labels, it turns out that one can make use of the distance transform or informal convolution to speed up the computation, and this reduces the time to compute the exact solution to n times d. And this is, of course, much faster. And in addition, if you have, for example, a GPU, you have parallel threads, you can reduce the time even further to n times log d, and d is the number of parallel threads. So how can we use this idea to decompose our image into horizontal and vertical chains and have a very efficient algorithm? So the idea is as follows. We want to minimize the sum of two functions, f1 of x and f2 of x. And it turns out that f1 will be the horizontal chains and f2 will be the vertical chains. The unaries usually are no problem. You can put it to one of the two functions, or you can split it up, whatever you want. So the unaries is not the problem. Just the interacting function which make it complicated. So the basic idea is now, and this is done in many approaches, if you give up that x1 should be equal to x2 here, you can introduce Lagrange multipliers that take care that both solutions coincide in the optimal solution, and this provides you a lower bound to your original problem, and this function is called d of lambda, and lambda is the Lagrange multiplier. And what we here describe is the following. So the minimization problem for this first part here with respect to x, which is independent of the second part because we split it up into two groups of variables, is called d1 of lambda, and the second one is called d2 of lambda. And the idea of the algorithm is the following. So the sum of d1 of lambda and d2 of lambda is complicated to maximize, to optimize, because there's these horizontal and vertical chains. But one of the two functions is easy to optimize, because d1 of lambda is just independent vertical chains, and d2 of lambda is just independent horizontal chains. That's easy to solve. And the idea is now that we first approximate the first function, d1 of lambda, with a simpler function, such that the sum of both can be solved easily. And then we do it vice versa. We approximate the second function with a simpler function, and such that the sum of two functions can be solved. And when does this work? And this is based on a very classical principle, which is called majorize, minimize. And here, since we are maximizing dual, it's called minorize, maximize principle. So it means we need to find a minorand d underbar 1 of d1 of lambda, and then if we can solve this joint problem and we do this sequentially, then we have a guarantee actually that we monotonically increase the dual energy. So and for these functions d underbar to be a valid minorand, what is necessary? First of all, it has to be smaller than d1, and for all lambda, and at lambda k, of course, it has to coincide. So you can see this in this graph. At the point lambda k, it has to coincide, and for all other lambda, it has to be smaller. And this gives you a guarantee of monotone S-center. So the question is, what are useful minorands? And I already mentioned before, if you have only unary terms, this does not cause any problems. So therefore, the idea is we try to approximate this function, for example here d1 with this minorand d lambda, with a unary function. So it means we try to find a unary function that is below the original function, because the unary terms can be easily taken over to the other function such that they can be optimized jointly. And we are also interested in maximal modular minorands, which means that there is no other phi prime such that this expression here is less than this expression using phi prime here. Of course, there are different possibilities to find this maximal modular minorand, so it's not a unique solution to that. And our strategy is to remove as much as possible unaries from this function to the other function, because if we can remove as much as possible unaries, then we somehow get the best minorant to that function. So here's the general strategy, which more or less gives you an optimal minorant, in the sense that the unirays are spread uniformly. So for the first, we might assume without loss of generality that the minimum value of the function is 0. If it was not 0, we can remove it, the minimum, and add it back later. But here we assume it's 0. And the second part is that we identify a support function h, which is not, or that holds, which is 1 for all labels which are not part of the optimal solution. Because here we can remove something. So it means HIK, so I is the node and K is the label, is 1 if, when we fix this label IK to be 1, the energy is larger than 1, so it's not optimal then, because we assume the optimal solution is 0, and it's 0. So it's an indicator function that tells us this particular label for this node is not taking the optimal solution. And now we can find a maximal monotone minorant with respect to this H by solving the following problem. We try to find a maximal epsilon such that epsilon times this support function H transpose X is less equal to our original function. So this is, whenever I write transpose, so H transpose X, it means this is a modular thing, because it's just really vector. And this problem, of course, has to be this constraint has to be valid for all X. And in this form, it's not so easy to solve. But there's an equivalent formulation, maximizing epsilon for all X, such that this helps. So we first divide by H transpose X. So epsilon should be less equal f of X over H transpose X. And if this has to be valid for all X, we can also try to minimize the upper bound, which means we try to minimize this ratio of f of X over H transpose X over X. And this gives the equivalent epsilon. What is important that if we remove epsilon times H transpose X from our function, this preserves the minimizer. So we just reparameterize our function, but the minimum stays the same. And this has then be taken over to the other function. And when you look at this problem, this is a well-known problem. It's a minimum ratio cycle problem. So you can use, for example, the algorithm that has been proposed by Laura in '66. And it works as follows. You need to pick a large enough epsilon 0. Then you solve this minimization problem here. So you see it's just based on chains, because f is always a chain-based function with additional unitaries. And then when you solve this problem, you compute the epsilon k plus 1 based on this ratio, and the algorithm terminates as soon as this difference here is 0. So once we have done this, it doesn't mean we are finished. So when we remove epsilon 1 times h1 from our original function, the minimum stays the same, but it doesn't mean that we cannot still remove something more. So we can repeat the whole procedure, again identify the support function of nodes where we can, which are not part of the optimal solution, and do this again. And we do this until the next support function is 0. It means we cannot remove anything more. And the maximal modular minorant is then finally given by summing up over all this epsilon t times ht. And you have the guarantee that this is a minorant, maximal modular minorant to your problem. So as I mentioned before, if the minimum of our function was not 0, we can simply remove it and then add it back to the minorant again. So here's a simple example of a Potts model. So what you see here in the circles are the unary costs, and it uses a Potts prior. That means that the cost of each edge between nodes is exactly 1 for all the edges. So it's very easy to see that the optimal solution goes here. So this costs nothing, nothing, nothing. This costs 1, nothing, nothing, and this costs 1. So the total cost is 2. And it means the first support function is made of all these nodes here, which are not connected with this blue line here. And if you apply this approach, the maximal modular minorant, okay, something I would mention before is the cost of the optimal path is 1 plus 1 is 2. So we first need to remove 2. And then once we have computed the minorand, we add it back again. And the valid maximal modular minorand for this problem is given with this graph here. And you see that the cost of the optimal path is 0, plus 2 is the same. And you can check different solutions to this problem here, and you will always see that it is smaller than the original one. So, okay, this was the optimal strategy, but it turns out in practice it's too costly to have an algorithm that works very fast. And therefore, we have implemented different heuristics that are inspired by this uniform distribution of the slacks. There's one particular approach, still a heuristic, which works very well, is obtained from a hierarchical approach that tries to approximately uniformly distribute the slack of the nodes. So this is very tricky, and I think only Sasha really knows the details how this works, because he tried to optimize all the memory accesses when this is implemented on the GPU, such that you can get the best out of that. But it's highly efficient, so it can be computed in n log d time using deparallel threads. So when, for example, compare this thing with TRWS, it uses the same number of memory accesses, but is easier to parallelize. So now back to the algorithm. So now we have an algorithm for computing a minorand. Might it be the optimal one or a heuristic? We propose to use the following minorand. So this d underbar is given by the minimum with respect to x of the maximal modular minorand of f1 plus lambda k minus lambda k plus lambda. So the whole thing here is modular, and so it's transpose times x. So now let's check if it's really a minorand. So the first thing we need to check is if it's smaller for all lambda. And the second one is that it has the same value at lambda k. So it's quite easy to see if you have this inequality here that it's smaller, because you see here we use the plus lambda k minus lambda k, so it's 0 here to compare it with the left-hand side, but it's easy to see that since the first two parts here are approximated with a minorand, it's a valid minorand for all lambda. And at lambda k, what do we have? At lambda k, you see that lambda is lambda k, it cancels, so it's just a minimum with respect to x of this minorand here. And this is actually exactly the same as the original problem, because in our construction we made sure that we do not change the optimum. So we only removed things which do not change the optimal solution, and we add back the value of the optimal solution. So now solving for the iterates, the question is, what's the best ascent for the method? So we need to solve the following problem. It's the d underbar, the minorand of the first term plus the second term. And now we insert again the expression for this function here, which is minimum with respect to x of this part and minimum with respect to x of this part here. And of course, an upper bound to this thing here is that we do not minimize these parts individually with respect to x, but we minimize the whole sum of them. So it gives you an upper bound to your problem. And then it's easy to see that this lambda here cancels this lambda here. So it's exactly this problem you're minimizing, which provides you an upper bound. And the question is, can we reach exactly this upper bound with an update step? And so what we would like to have is, we would like to find a lambda such that this expression is equivalent to this expression here. And it turns out that exactly setting lambda to the negative of the first part gives you 0. And then you replace this lambda with this negative expression, you exactly arrive at this problem here. So you can exactly reach the upper bound by making this update here. And you see the update is very simple. So the new Lagrange multiplier is given by the old Lagrange multiplier minus the minorand. So you just need to compute the minorand, that's everything, and subtract it from your multiplier. And for the second update, you get a similar update scheme. So when you more carefully investigate what you're doing here, it turns out, so if you group your Lagrange multipliers into horizontal and vertical one, it's nothing else than a block coordinate ascent on horizontal and vertical variables. So what about the convergence? by construction, the DMM, dual minimize maximize algorithm, yields a non-decreasing sequence of dual function values. But still, of course, it may get stuck in non-optimal solutions. So that's still a problem. Since we are maximizing a piecewise linear function, we have no guarantee that we find the globally optimal solution. However, in practice, it turns out it works very well. So for many problems, we see actually that the gap is 0. So how can we recover from the dual solution, the primal solution? We just need to run horizontal or vertical chain problems, the dynamic program, and since this now uses the Lagrange multiplier, this gives us one of the feasible solutions then. So here's a comparison with Vladimir's algorithm, TRWS. And what you see here is the dual objective, the lower bound, and the red curve is our algorithm, and the blue curve is the TRWS. And here we compare comparison, which means a whole sweep over the image. It turns out that our algorithm is very fast in the beginning, and then it's overtaken by TRWS. But in the end, for example, this is very slow. We don't know if it also finds the globally optimal solution, but our algorithm here finally finds the globally optimal solution, so with 0 gap. However, in practice, we use only 5 to 10 iterations. So the region where we are interested in is somewhere here. So in here, you see that this parallel version works quite well. So this is the number of iterations. Now let us compare the time per iteration. So one of the advantages of this algorithm is that it can be implemented on the GPU. TRWS is a sequential algorithm, which is not so easy to parallelize. You can do it with diagonal parallelization, and there are also hardware implementations you can find, but it's not so easy and does not fit so well to the GPU. So for relatively small images, you see that the speed up on the GPU is not so much, 4 point something compared to to the baseline, which is just on one CPU. But if you have larger images, you see that one iteration here is has a speed up of almost 30. And still, we see that, for example, to reach the same energy here, we need much less iterations. So in total, it's really very fast. So you see, for example, here, this is a 1,000 times 1,000 image with 128 labels. One iteration takes 1/30 seconds. So it's really fast, each iteration. You need 5 iterations. So it's almost real time, even for these big problems here. So now I talked about the algorithm, which we will use for inference, also for learning. So how can we learn? So ideally, the idea is the following. These are the input images. This is the convolutional neural networks. This has a lot of parameters that extract the features. The features are correlated, and we run the CRF, and the prediction of the CRF is compared with the ground truth. This could be the ground truth image here. This gives us some error, and we try to minimize the errors. And it means we update the model parameters in order to get a smaller error. It's a typical bi-level optimization problem. So here written formally. So we minimize some loss function. X of theta is the prediction of the CRF. Theta are all these parameters of the CNNs. And x of theta should be an arcmin of our CRF. So the problem is that the lower level problem is discrete. So the gradient is 0 almost everywhere. So it's like a staircase. So actually we cannot backpropagate simply a gradient. It doesn't work. And actually what we're doing, we're applying the same trick as in the support vector machine. So if you have a 0-1 loss in the support vector machine, there's also a problem. And this is approximated with the hinge loss. And more or less the same trick is applied here. And this is known from the literature as structured output support vector machine of Zochan-Titris and co-workers of 2004. So how can we construct this surrogate loss function that can cope with this combinatorial nature of our problem? So here we have the loss function, and we try to find the upper bound to this loss function. So we consider the maximum of this loss function, and here we still assume that x is contained in the set of minimizers of our CRF. So this thing here is equivalent to this thing here. And then we apply a number of relaxations. The first relaxation is that we say, okay, we're not requiring that x is really a minimizer. We say that the energy of x should at least be as good as the energy of the ground truth solution. So we say that if we plug in the ground truth solution in our energy, it gives us hopefully a low energy, and we say, okay, the energy of our solution we want to compute should be less equal. That's the first thing. Okay, so we give this up, and therefore we have a less equal because we're maximizing over that. The second thing is to observe that the energy of the ground truth is larger than the energy of the optimal solution. It means what we can do, we can just add the difference of both. It again increases our upper bound with the same constraint, and then finally we drop this constraint. And we end up with this problem. And when you consider this problem now, what is it doing? It has the loss, it has the energy of the ground truth solution minus the energy of our solution we want to infer. And maximizing this thing here with respect to x can be done because we want to minimize energy, so maximizing a negative energy is exactly the same. And it turns out to be you minimize a loss augmented conditional random field. So f is the conditional random field. You subtract the loss, which is only based on unaries, so it does not change your problem. So it doesn't make it more complicated to solve it. And this x bar is then used, and this total maximum here is then our surrogate function. So it means computing the upper bound requires to solve this CRF with loss augmented unaries. So I have also a figure for that. So for example, this is our function for which we want to compute the minimum. Just computing the inference would give us this solution here, but now we augment it by the loss, so we subtract our loss. The loss in this case is truncated absolute. This is this dashed function here. And if you subtract it, the optimal solution is of course this red point here, because it lies below the loss function. And exactly this is this function here, and now for this function this is actually piecewise linear, and we can compute the gradient of this function, or the subgradient to this function. And it turns out that the gradient of this function here is exactly, what is it, positive or negative? It's positive at this solution here, at the ground truth level, and it's negative here at the point where you have violated your loss augmented constraint here. So it tells you somehow that the unaries for your problem at the ground truth level should be decreased to make it more likely that you get the unary solution. And here at the current point where this is the computed, the solution you have actually computed minus the loss, you should increase the unary terms. Okay? And this loss function here can be interpreted as a margin. So it means the energy should be larger than your current energy plus the margin. Okay, so now what about training? So now we have actually a loss, or it's an approximation to the bi-level optimization problem, and now we can start applying as, yes?
Here you say it's abstract this right now, but in the end it's theta, the variable. You would like to...
In this it's not linear, it's just, okay, I did not mention it, just with respect to the unaries, it's piecewise linear.
Okay, and what about theta? Because in the end it's theta.
Yeah, of course, then you have to apply the chain rule, and you have all these non-linearities. So here I really stop at the unaries. So with respect to the unaries, it's piecewise linear.
Okay, so then you can...
For example,
like
if you just want to... Exactly, yes. Yes, you make a back propagation of this gradient and further through the network. But for example, if you have just linear parameters like regularization parameters, then the overall problem is convex actually. So this gives you up to the level of the unaries, it's a convex optimization problem, the learning problem. Then of course it's nonlinear and so on, then it's no longer convex, but up to here it's convex. This is more or less what they're doing in the structured support vector machine. Okay, what about learning? So in order to speed up learning, what we're doing, we first train the CNN alone with some different loss, because to get a reasonable initialization. And this is the typical learning curve you are seeing. So this is on the training side, this is on the validation side. And that at some point we add the CRF to our problem. This can be seen as a particular dynamic programming layer, if you want, in the network. I like to have the view that the convolution neural network is just a data term to the CRF, but you can interpret it also vice versa. And you see that there's a huge performance increase once you add the CRF, because the smoothness cost really, yes?
So when you train it a lot alone, you mean you don't regularize, you put the ground truth?
Yes. You can also view it like you use a CRF that has no pairwise terms. It's the same, more or less. You switch off the regularizer, and at this point here, you switch on the regularizer, and this really tells you, although it's just a very efficient, simple layer, it gives you a huge performance boost. So learning is performed using stochastic subgradient descent with momentum. So it's standard in learning. And as I said, first we do a CNN only pre-training and followed by joint training. So what I did not explain, but what we did very similar, we also trained the pairwise weights. So this function I showed in the beginning, the edge weights, are also based on CNN, and a similar approach to this one also works for the pairwise terms. So now we can have a look at different databases, how well it works. So this is with 3 layers, very shallow. This is with 7 layers. Only the CNN gives you an error of 23. Then if you just add the CRF without joint training, it decreases to 11. Then if you do a joint training, it decreases down to 9. And then if you add the pairwise, it also gives you a little bit of performance increase. On this particular data set, not so much, but for example, on this data set or on this one, it helps you more. So here are some qualitative results. So this is a typical sequence of the recent Middlebury database, for which you have a very accurate ground truth. This is what you get just by descriptor matching from the CNN, very noisy. Here you switch on the CRF, but no joint training. And if you do a joint training, you get this result here. You see here in the error plot, a lot of errors, less errors, but joint training really, for example, look, it can help you to reduce the error even more. Here's a detail view. So CNN only plus CRF and joint training and pairwise, and you can even recover very small details. And what is funny, although in this model occlusions are not explicitly modeled, it turns out that it can most of the time almost exactly recover occlusions if they are not too big. For example, there are a lot of occlusions on the left-hand side here. They are perfectly recovered, although they are not modeled. But we're currently working on an extension of the model towards occlusions. So we of course, to have a paper at CVPR, you need to evaluate like crazy. So this is what we did. And it turned out we are not top-performing method because we did not apply any engineering. We really took the result of the CRF, and we did not do a smoothing or outlier, nothing. We really took the result of the CRF and evaluated it, and it turned out that I think it was place 15 out of 100 or so when we inspect the so-called bad 4 or 2 error. But the funny thing is, if we inspect the root mean squared error, we were among the top 3 methods. So I think it's, where is it? The error. Okay, here's the, okay, this is root mean squared error. It turns out it's place 4.46. So, and it's not the exact rank, but it's under the top 3 performance method. And also it works very well on Kitty, not a top performing method, but as I said, we did not apply any engineering to that. What is really funny is the following. For example, on Kitty, the ground truth, Kitty is for autonomous driving, the ground truth is not so good. Look at these results here. Here's the ground truth. So the ground truth is only available in part of the image. For example, here in the background where you have black pixels, there's no ground truth available. This is the result we're getting. It's very sharp because we have these pairwise terms that stick it to the edges. And this is the result of top performing methods. So it seems the CNN only methods, they really learn the ground truth, so such that they work well on the data set. So look, for example, here that we have very accurate boundaries, but we make a lot of mistakes actually on the left-hand side. So this is counted in the metric. So they are purely overfitting to the mistakes in the ground truth. And here's also one example where we have very good results. And this is one example where we have bad results. And one of the reasons why sometimes the results are not so good is that on slanted surfaces, since we have a discrete solution, we make a lot of very small errors. And this, of course, counts in the metric. The last artifact with the discretization can be easily reduced by making a smoothing of the final result, because the zero F finally gives you again a cost volume. And what you can do is you can simply fit the parabola to the final cost volume and minimize the parabola, and then you get much smoother results. And it turns out that it decreases further your error, but we did not evaluate this method because we didn't want to apply such tricks. But you can make it easily more smooth by this trick here. Okay, so this was for stereo. Now let's move to optical flow. This is a recent paper. So what is the problem with optical flow? So now we were talking about stereo matching, and the cost volume you need to compute for stereo matching is three-dimensional because you have just 1D labels. So the space complexity is of order width and height times number of labels, which is still okay. But whenever you go to optical flow, you have here this nasty D squared. So it means for reasonably large images, 1000 times 400 with 300 labels. For stereo, no problem, 0.5 gigabytes fits to recent GPUs, no problem. But this is still too much even for state-of-the-art graphics cards in computers. So there's really a problem. However, for training and zero F inference, we somehow need to have the cost volume in the memory, so we need to do something here. So the zero F model we consider for motion is a straightforward extension of the model of stereo. The only thing is that now we have here again a pairwise time between horizontal and vertical displacements. So this Fi is now not longer a vector for matching costs of different disparities, but it's a 2D slice of matching costs for horizontal and vertical displacements. But the observation here is that actually the regularizer, so this is for the horizontal displacement, this is for the regularizer for the vertical displacements, it's separable. There exists some work that solves the full LP relaxation, so using TRWS. There's a work of Chen and Koltun, and they found that on a multi-core GPU with hundreds of gigabytes of memory, it's somehow feasible. One iteration takes, I don't know, at least 1 minute or so, but it's doable. And what we propose is to use a weaker LP relaxation, which is based on work of Alexander of 2008, quite old work. And it actually splits your optical flow into two independent problems, horizontal and vertical, and then links the two problems via an additional edge. So this is maybe better seen here. So this is the original problems where the labels are 2D displacements and the matching costs are on the labels. So for example, if you have 3 horizontal, 3 vertical labels, you have a total of 9 labels. And we split it up into 2 problems with only 3 labels horizontally, 3 labels vertically, and then introduce an additional edge, and the cost of the descriptor matching now lives on the edge. And it turns out that while this approach has order of number of nodes of the image times D squared memory, this only needs order of nodes times D memory. So we have more or less reduced our optical flow problem to 2 stereo problems, if you want. And they are linked with each other. We still need to compute an exhaustive matching in the 4D volume, but you will never have to store the complete 4D volume. And the Lagrangian decomposition now looks a bit more nasty. So you have the horizontal component, which is decomposed into chains, the vertical component, which is decomposed into chains, and there are cross edges that link those 2 approaches with each other. And for each of them, you need to introduce Lagrange multipliers. And the dual problem now, of course, depends on these Lagrange multipliers. And it turns out you can implement a block ascent method here. There are some outer iterations of the algorithm. In the inner iterations, we more or less solve the stereo problem in one plane. Then we pass the slacks to the cross-linked edges. Then we do the same for the other plane, and so on and so on and so on. So what about learning? learning is really complicated in this case. Let us first consider the problem where we ignore the zero F. We just want to do learning with the convolutional neural network with the idea of predicting two 3D volumes. And in this case, we use a min projection. So it means we compute one cost volume, which is called CU2 of U1. So where we minimize with respect to the other displacement. Okay, so you can see this as a kind of a relaxation. And we do it also in the symmetric way for the other cost volume. So we have another cost volume that depends on the vertical displacement where we have minimized out the horizontal displacement. So it means here we have our image. This computes the descriptors, the same for the second image. Then we correlate those, but we only store 3D volumes because we have minimized out in this case with respect to U2, and here we have minimized out with respect to U1. So this gives us, of course, a better space complexity, and it turns out exactly this structure will then be needed by the zero F relaxation. However, the time complexity is still order of d squared. So m is number of it's a dimension of the feature vector. However, what we have observed is since we are using the tan h function in the nonlinearities, the final feature vectors are almost binary. So therefore, what we can do is we can binarize these feature vectors and then use only bit shift operations in order to correlate them. So it means, if, for example, if you have a 32-bit float, you can have a speed of 42 if you just use bit shift operations. However, one problem is for learning, if you do this binarizing here, that's really a problem because you cannot backpropagate an error. But we have also a solution for that. So what we still are not able to do this joint learning with the zero F. This is still not possible, so we are working on that. However, what we are doing here is now we just learn the descriptors based on this construction and then put it together with the zero F and then see what comes out. So we have actually 3 different approaches to cope with the binarization. FF means no binarization, it's very slow. So for example, the matching takes 4 seconds. Then QQ means binarization, and when backpropagating the error during learning, we simply ignore it and use just identity. This is called straight-through estimator in the literature. Is this one? It's much faster, as you can see, but also the error increases. And there's some hybrid model that uses binarization only in the min projection. So only when you do the exhaustive 4D, actually you do the binary matching, but you again use the floating point volume in order to compute the cost volume. And this is some nice intermediate thing. It's faster and it gives you also reasonable error. So here are a few results. Now using the C and N without the zero F. So this is 2 typical sequences. The first sequence is very easy, small motion. And the second sequence is very complicated, it's dark, and there's a large motion inside and a lot of occlusions, as you can see. So it's really hard, this scene. And this is the corresponding ground truth. Since it's a synthetic video, you have perfect ground truth for that. So I can repeat this. First one is easy, and the second one is very complicated. So when you do the learning with the FF approach, so no binarization, it works reasonably well. So here in this phase, still no regularization is used. So the endpoint error, so root mean squared error is 1.8 on average. Then here of this more complicated scene, it's of course much larger because there's huge occlusions here on all sides and so on. When we do the hybrid learning, the error is almost the same, but it's much faster. And if you do the binarized learning, then you see that actually you get much worse results. So now what we did, we now attach the zero F with this particular relaxation to these learned cost volumes. And we compare the time we need to solve the problem. So in the FF method with the floating point cost volumes, it takes 24 seconds for this size, so it's still a huge problem. And if you do the binarized descriptor matching, it's much, much faster, as you can see. When we compare this to the state-of-the-art, one of the state-of-the-art methods only can apply their method to 1/3 of the resolution. So in this case, we are 10 times faster. So here's the result now using the learned descriptors together with the CRF inference. This is with floating point descriptor matching, works very well. And the funny thing is when you do the quantized descriptor matching together with the CRF, the error is almost the same. So it does not get worse too much. In order to get nice results, what people are usually doing, they take their result and then they do a back matching to identify outliers in the solution, and then they do some in-painting of the final volume, and there's an approach that is called epic flow. We did not put this to the paper, but here I'm presenting you results. So when you have this result, you identify outliers and you do an edge-based in-painting, similar to what Joachim is doing for stereo maps, you get much better results. So you see that the error here is 0.2, so almost perfect, and here it goes down to 4.4. So it gives you really much better results. And when you compare this to the ground truth, you see for the first image it works very well, and for the second image, since there are fast moving parts, small details, and a lot of occlusions, of course you're missing something. So finally, there's a video showing on more images how this works. So this is now without in-painting, still having some outliers inside. So the average computation time, I think, for this type of images is around 1 second. But remember, these are 128 squared labels we need to solve. Okay, so the final evaluation on the Sintel database tells us that with this post-processing, we are on place 26 out of more than 100. It's reasonably, so if you compare the numbers, there are a lot of approaches almost having the same error. And if we only evaluate the error in the non-occluded pixels, then we are currently ranked 10 out of more than 100. So it more or less tells us that we need to explicitly model occlusions to make the whole approach work better. We also tried it to apply to completely other databases, the old Middlebury database, for example, and it works out of the box very well. So we think because we don't have so many parameters, it's not overfitted to a particular database, therefore it works very well also for other data. So to wrap up, I was talking about CRF-based models for motion and stereo, and we tried to learn more or less optimal descriptors to compute data terms and also edge weighting functions. And in order to make the whole approach fast, we developed a highly parallel minorize maximize dual algorithm for the CRF, which really works very well. The code can also be downloaded. And for learning, end-to-end learning in stereo, we used a surrogate loss that is inspired by the structured output support vector machines. Of course, there are many open questions. So really, for me, the striking question would be, the dual problem is piecewise linear, and so you may get stuck in a non-optimal solution. So it would be interesting to somehow construct a dual problem which is smooth. Okay, it's no longer the original dual problem, it's a smooth problem, but then you, of course, you have the guarantee to get to the optimal solution and you can apply acceleration. But it's really not clear how you can do this while keeping the simplicity of the dynamic programming. So how this is only very efficient because you can compute the ascent with dynamic programming, but it's not clear how you can do this for a smooth problem. How can we do end-to-end learning for motion? Not clear so far. And we are currently also working on better models incorporating occlusions or higher order smoothness. I think if you would have an efficient CRF model with higher order smoothness, piecewise linear, whatever, then you will almost get perfect results. So I think that's really very, very good. And finally, a bit more far-reaching. When you consider what the dynamic program is doing, it computes sums and takes minima. So you could try to generalize these operations, generalize sums by weighted sums, replace minima by some weighted soft minimum or whatever, and try to learn what really the dynamic programming is computing. So you don't have to specify exactly the shape of your energy function, but try to learn that from data. That would also be interesting. Okay, thank you very much.
arrived a bit late, so I hope you didn't say anything about that. You didn't compare with non-learned approaches. So like
I mean, implicitly, because on the database they are very low ranked. So I did not show the numbers, but
so that's already done.
yes. For example, one of the initial experiments was you can code the census transform with a CNN very simply, and then you start learning from that initialization. Then you immediately see how it transforms and gives you different descriptors. So you actually see that it's not an optimal thing using a census transform. So it was one of our first experiments to see how it works.
Okay, so if there are no more questions, then we have a coffee break, and thanks again.
Vladimir,
yeah.
So I wanted to confirm, is a unique maximal linear numeron?
No, it's not unique. It's not unique, no. So here we try to spread the select uniformly, because then you have the hope that you will have the faster conversions, but it's, of course,
So
it's
the
not.
procedure where you first do epsilon 1, epsilon 2.
Yeah, exactly.
So it just finds a maximal.
It finds a maximum. What you're doing right.
Yeah, I don't see anything. Thanks again.